Hi everyone, how are you doing? Hello Ajay, hi Sonam, hello Kavya. So now let's just get started. So we were discussing, right, diagonalization, as you know. So do you remember what we were discussing in the diagonalization? So let me just quickly remind you that we were saying that if you have, let's suppose a matrix A, right? If you have a matrix A, and then if you want to represent this matrix A, then what you can do, I mean, for any random matrix, it need not to satisfy any property. For any random matrix A, what you can do, that ax equal to lambda x, that's what we know if there is only one eigenvector, right? Or you write it like this: ax equal to x lambda. Is this fine to everyone? Now what we can do, we can write all set of eigenvectors like this, okay? Av, okay, or au, whatever the notation you want to use. Av equal to, earlier it was x lambda, so v, okay, the eigenvectors, set of eigenvectors, and then lambda. Is this fine to everyone? So that's what we have studied. Should I go back to the previous slides and tell you that what we were studying? So uh, just a second. So I think this is what we were studying. See here, right? AB equal to V lambda, and this is true for any matrix A. But now suppose that you have this V, which is a matrix of eigenvectors. V is a set of linearly independent vectors. Suppose this V is a set of linearly independent vectors. In that case, what you can do? In that case, if U inverse or U or V, whatever you like to call, if this U inverse exists, then we can write it in this way. Okay, and that's called eigenvalue decomposition. Okay, so if U inverse exists, then you can write it in this way. Okay, that's what we have studied yesterday. Now let's just see few more questions apart from the questions that we have seen yesterday. Okay. Okay, so what we have seen is that if you have, let's suppose if you have A as a matrix, right, then you can write it in this way: AU or AV, whatever you like to call, equal to U lambda, and then A will be U lambda and U inverse, right? Or maybe V lambda and V inverse. Here A is, since we are talking about eigenvalue and eigenvector, so that's why A is square matrix. A is a square matrix, isn't it? And then if it is a square matrix, then there will be n linearly, sorry, n eigenvalues may be repeated or something like this. If it is n cross n, then there will be n eigenvalues. Maybe some are complex, some are, I mean, that's fine. Okay, complex and these things are fine. Complex are real numbers, but there will be n eigenvalues. So this is also a square matrix, and this is, I mean, every matrix is a square matrix here, right? This is also a square matrix. Okay. Now let's just see how to diagonalize. Okay, this is also called diagonalization. How to diagonalize a matrix A, right? Which means find out this U and lambda. So how to find out this U? U is just a set of eigenvectors, and lambda is set of eigenvalues. I mean, eigenvalues here. So if you want to diagonalize this, then you need to find out that whether, first of all, is this diagonalizable? Let's just check. Okay. How to check it is diagonalizable? Do you remember? Any matrix is diagonalizable if and only if it has n linearly independent eigenvectors, isn't it? So let's just check quickly if you can find n linearly independent eigenvectors here. So what are the eigenvalues? Can you tell me? What are the eigenvalues? Eigenvalues are repeating, right? 2 and 2, because this is a upper triangular matrix. So here the eigenvalues are repeating 2 and 2. Now, how to find out the eigenvector? See, ax equal to lambda x, right? So basically, you need to find, you can say that a minus lambda I into x equal to 0, right? So basically, you need to find the solutions of a minus lambda I. And lambda is 2 here. So if lambda is 2 here, then you need to find solutions of a minus lambda I, means that 0, 1, 0, 0, right? Into x. Okay. So what are the values of x1, x2 that satisfy this? I think you can find out. Let me just go to next page. So this is 0, 1, 0, 0, and then you need to find x1, x2. This is 0, 0, right? So you can say x2 is a free variable, which is k. And then if x2 is a free variable, then what is the x1? Sorry, x1 is a free variable. X1 is a free variable, which is k. Let me write it free variable, right? And what is x2? So you can easily figure it out that x2 will be how much? X2 will be k, right? So x2 will be, sorry, x2 will be 0. X2 will be 0, right? So k into 0. This is this is how many vectors you have got? One vector, two vector. So this is eigenvector basically, right? This is eigenvector corresponding to lambda equal to 2. Okay. So yeah, this is just one linearly independent vector. Okay. So this is just one linearly independent vector. If you have just one linearly independent vector, can you diagonalize this matrix? No, right? So that is why diagonalization is not possible in this particular example. Now let's just go to this part B and then we will see part C also. Okay, let's just quickly see part B and then we will see part C also. Okay. So here, if you find out the eigenvector, so let's suppose the eigenvalues are already known. Now, if you find out the eigenvector, so what is the eigenvector corresponding to lambda equal to 1? It will be 0, and then it will be 3, it will be 3, then minus 3, then I think minus 6, then minus 3, then 3, and then 3, and then 0, right? And then 0, 0, 0. So let's just see how many eigenvectors will be there. Let's not find out it. Okay, I mean, I will just see that, okay, if it is diagonalizable or not. So how many linearly independent eigenvectors? Maybe I need to do a row reduction here, right? Okay. So probably I think we can do it, but it might be there. Okay, one diagonalization is as follows. So basically, this is the matrix, right? This is the matrix given. Now the eigenvalues are given to us, which is 1 and minus 2. I think minus 2 is repeating two times. Okay, minus 2 is repeating two times, and then you can find out the corresponding eigenvectors. Okay, corresponding to minus 2. So I think corresponding to minus 2, these are the two eigenvectors we are getting, and corresponding to 1, we are getting this as an eigenvector. Okay, so maybe for one of them we can find out. Okay, so can you find out the eigenvector corresponding to 1? You need to shuffle first. Maybe let's just shuffle it. So it will be 3, 3, 0, and then 0, and then let's suppose it is minus 3, minus 6, minus 3, and 0, and then 0, 3, 3, and then 0, right? Okay, now maybe you can add these two, and then this will be finally 0. Okay, so let's just quickly add these two. Now maybe let me write it here. This is 3, 3, 0, and then this is 0, minus 3, minus 3, 0, 3, 3, right? And 0, 0, 0. And then I think if you add these two, this will be 0, right? So this is one pivot, this is again pivot, and then this is anyway 0, 0. Okay, this is also 0, 0. So finally you can say x3 is 0. So x3 is one of the variable which is 0, and then minus 3 x2 minus, sorry, x3 is k, and then minus 3k will be 0. So from here x2 will be, I think, uh, minus k, right? Minus k, and then x1 will be 3x1 plus 3k, 3k equal to 0, and then I think it will be k. So it is 1, minus 1, and 0. Is this what you are getting? Corresponding to lambda equal to 1. Sorry, not 0, it is 1. So this last term is 1, right? 1, minus 1, and 1. Okay, so this is the eigenvector. I mean, this is the only one linearly independent eigenvector that you will be getting. So this is corresponding to lambda equal to 1. Okay, so corresponding to lambda equal to 1, you got it. And then similarly, you need to find out corresponding to lambda equal to uh, lambda equal to 2, sorry, minus 2. And let's suppose this is repeating two times. So you need to, I mean, you will automatically be getting two linearly independent eigenvectors corresponding to lambda equal to minus 2. So if you do it, then you will be getting this and this. Okay. These are the two eigenvectors that you will be getting corresponding to lambda equal to minus 2. This is one eigenvector that we have got corresponding to lambda equal to 1. So you arrange all the eigenvectors and then you will be getting your middle matrix, right? So which means U or P, whatever you like to call. And then finally the diagonalization will look like this. Okay. So what is the answer? Answer is generally U, D, U inverse, right? Now here, this U is nothing but the set of all eigenvectors. So first eigenvector, second eigenvector, third eigenvector, right? Now, if you're writing lambda equal to 2, I mean, eigenvector corresponding to, let's suppose, lambda equal to minus 2, then lambda equal to minus 2 will be here. And then minus 2, it should be in the same order. So what I'm trying to say, let's suppose, let's suppose you got corresponding to lambda equal to minus 2, you got the eigenvectors like this. Let's suppose you got, okay, minus 1, 0, 1. Let's suppose this is the solution corresponding to lambda equal to minus 2, right? Minus 1, 1, 0. Okay. And now corresponding to lambda equal to, let's suppose, corresponding to lambda equal to 1, we have got k into 1 minus 1 and 1. Okay. So these are the set of eigenvectors that we have got. So how to find out the eigenvalue decomposition? See, just see this carefully, that you have the eigenvalue decomposition or the diagonalization, something like this, right? So now this U, whenever you are writing this U, then it should be the ordered, which means if you're writing, let's suppose minus 1, 0, 1, and then minus 1, 1, 0, and then let's suppose 1, minus 1, 1. Then what is the D here? See, this minus 1, 1, 0, it is corresponding to which eigenvalue? Minus 2. So that's why minus 2. This is corresponding to which eigenvalue? Again, minus 2. So that's why minus 2. This is corresponding to which eigenvalue? 1, right? So that's why 1. So basically this diagonal and these things should be in the order. Okay. So Saurabh is asking, sir, is there any shortcut method to check whether the matrix is diagonalizable, except checking that, okay, there are linearly independent eigenvectors? No, there is no other method. Basically, we need to check whether these are linearly independent eigenvectors or not. Okay. So there is no other method. See here, I mean, in all the solutions, you will be finding that they will also be checking that whether you have linearly independent eigenvectors or not. For example, they are saying for corresponding to lambda equal to 2, there is only one eigenvector. So there are not two linearly independent eigenvectors. Okay. So they will also be doing the same thing. Okay. So there is no shortcut here. Got it? Now, now similarly, for this particular matrix, you need to do the same thing, right? So what are the eigenvalues here? Can anyone tell me quickly? This is lower triangle matrix. So what are the eigenvalues? 3, 2, 2, and 3, right? 3, 2, 2, and 3. So you have the eigenvalues and then you need to find out the eigenvectors. It is not diagonalizable. It is impossible to find the basis uh, using the eigenvectors. Okay, so here also the eigenvectors are not linearly independent. Okay, so let's just quickly check it whether the eigenvectors will be linearly independent or not. I think this is very easy to check. How? See here. Corresponding to lambda equal to 3. How many eigenvalues are there? Lambda equal to 3 and lambda equal to 2. So let's just see first corresponding to lambda equal to 3. It will be 0, 0, 0, 0, right? Okay. Now 0, and then if it is 3, then it will be minus 1, 0, 0. Again, so basically there will be two rows of 0, 0, 0. And this is 0, 0, minus 1, 0, and 0, 0, 0, 0, right? Okay. Yeah. So sorry, this is 1. This is 1. Now, what are the free variables? I think this is pivot, this is pivot. This one is free. So how many free you have got? How many free you have got? So one free, right? One free means only one linearly independent, right? Linearly independent vector. Do you remember this? It means corresponding to lambda equal to 3, you have just one. Okay. But we need at least two because it is repeating twice. So if it is repeating twice, we need for everyone, we need one. Okay. For this three also, we need one. So that's why there is no linearly independent eigenvectors. Got it? Okay. Now let's just see this. This is a true false question. In this problem, if the statement is always true, then circle true. Okay. If A is 3 cross 3 with this characteristic polynomial, then A is invertible. What do you think? No, right? Because lambda equal to 0 is there. So that's why this is false. Because lambda equal to 0 is eigenvalue. Okay. A is 3 cross 3 matrix with two distinct eigenvalue in the diagonal. Two distinct eigenvalues is diagonalizable. A is 3 cross 3 matrix with two distinct eigenvalues. Okay. So sometimes true, sometimes false, then M. So basically it may be, right? Maybe it is diagonalizable, right? So that's why M. Because it may be possible that with two distinct eigenvalues, you may be getting two linearly independent, may not be getting two linearly independent, right? Sorry, three linearly independent, may not be getting three linearly independent. If A is diagonalizable and B is similar to A, okay, then B is diagonalizable. So what they're saying that if A is diagonalizable, right? So which means let's just go to the next page and let's just see what they're trying to say. Okay, so if A is diagonalizable, mhm, just a second. Okay, so some people are saying, I think most of you are saying it is true. Why that is true? Can anyone tell me? Do you want to speak up and let me know? Anyone wants to speak up and let me know why that is true? If you want, you can unmute yourself and let me know.
Hello.
Yes, Aditya.
Sir, it's transitive, no? So if similarity is transitive, so if A is similar to some diagonal and B is similar to A, then B is similar to diagonal.
Yes, right. Nice. So basically, diagonalizable means that it is similar. Like I mean, other way of saying diagonalizable, it means that B is diagonalizable means that B is similar to some diagonal matrix, right? So A is diagonalizable means A is similar to some diagonal matrix. So, so let's just interpret it, step by step. So A is diagonalizable. It means what? A is similar to some diagonal matrix, right? Let's suppose D. Okay, which means A is similar to D. Now B is similar to A. So B is similar to A. It means definitely that B is similar to D. And B is similar to D is other way of saying that B is diagonalizable, right? Okay. Everyone understood that A is diagonalizable means that A is similar to D, right? Okay. A is diagonalizable means that A is similar to D. So, see, the diagonalizable means that it is similar to D. I mean, it is similar to some diagonal matrix. And then they're saying that B is similar to A. Okay, specifically they say B is similar to A. Then it means that A, B, and D are similar. Or if you want, as Harsh is saying, if you want, we can also use the formula of diagonalization. Okay. So, Harsh, you want to speak up?
Sure, sir. Uh, so A can be written as PDP inverse,
Yes. Right.
and B is similar to A. So B can be written as for some invertible matrix Q as QA Q inverse.
Okay. So B is similar to A. Then this is QA Q inverse. Yes. Right.
Or Q inverse AQ, anything is fine.
Okay. Which one you prefer?
This is fine, the one that you have written, sir.
Okay.
So then you can substitute first equation in the second one.
Okay. So basically, finally, from this, you can say B equal to Q inverse, and in between it will be PD P inverse. Yes.
Right, sir. So QP is the inverse of P inverse Q inverse.
Right, right. Very good. Okay. So from here also we can say that B is diagonalizable, which means that you have some matrix QP, and then you can write it that matrix into D into QP inverse, right? So that's how also we can prove it. So both are fine. Let me just call it method 2. Method 2. Let me just call it method 1. How many of you have done using method 1? Okay. How many of you have done using method 1? Using the the property of similarity. The diagonalizable itself means that A is similar to some diagonal matrix. Okay. So if A is similar to diagonal matrix, B is similar to A, then B is also similar to some diagonal matrix. How many of you did using method 2? Okay. Okay. Cool. Now let's just move to the next question. Okay. So now let's just move to the next question. I think this was true. A is diagonalizable, and then A and admits n linearly independent eigenvectors. So what do you think? This is true or sometimes true and sometimes false? Tell me. Yes, this is obviously always true, right? So false may be true, true and true. Okay. So let's just check the answer. False may be true, true and true, right? False may be true, true and true, right? Now let's just see this particular question, what they are trying to say. Give an example of 2 cross 2 real valued matrix A, each of the following, which satisfy each of the following property. A has no real eigenvalues. Okay. So can you give me such that A has no real eigenvalues? I think we did it in the lecture of eigenvalues. So just tell me something where A always rotated. For example, if you multiply by xy, then finally let's suppose you get minus y into x. Okay. Can you tell me something where you will be getting something like this? So you want minus y, x times this, y times this, right? So maybe this is 0, this is minus 1. So that's how you will be getting minus y. And you want x. So 1 times this, 0 times this, right? Okay. Yeah. So basically, if you multiply this matrix by this particular xy, then it is always rotating it because dot product of these two is 0. So it means both are perpendicular to each other. So this matrix is always rotating by some angle. Okay, here it seems like 90-degree, but that's fine. If this matrix is always rotation, okay, always rotating, in that case, what you will say? Can there will be the real eigenvalue? Can there be the real eigenvector first of all? Can there be a vector which stay on the same line if you multiply by the vector multiply by the matrix A? No, right? So basically it will be get rotated, right? Which means AX will be this. If this is X, then AX will always be this matrix is such that it always rotate every particular vector. So basically it will not be having you can even verify this. It will not be having the real eigenvalues. Okay, it is easy. A has the eigenvalue 1 and 2. It's very easy. Can you tell me? Yes. So just 1 and 2, right? Just 1 and 2. A is invertible but not diagonalizable. Okay. Or A is diagonalizable but not invertible. This is very easy. A is diagonalizable. This is a diagonal matrix. In fact, it is diagonalizable. Diagonalizable means it is similar to some diagonal matrix. Is this invertible? Obviously not, right? A is invertible but not diagonalizable. So here, I think we had examples previously also, right? Where the matrix is invertible but not diagonalizable. Do you remember? So I think the same example we can give. This kind of example we were having. So this matrix 1 1 0 1, okay, is invertible, but it is not diagonalizable. Okay. So basically, you just make sure that finally, I mean, whenever you are making the matrix, just keep it 0 and 1. Okay. I mean, keep it as simple as you can. And finally, you know that, okay, the eigenvalues are 1 and 1. So it will be 0, 0, right? Whenever you want to find out the eigenvectors, so you will be finding the eigenvectors something like this: 0 1 0 0. Then there is only one free variable, right? This value is not getting destroyed, so there is only one free variable, so it will be just one linearly independent. There won't be two linearly independent, right? And definitely it is invertible, so only one linearly independent eigenvector. Anyway, last time also we have given the counterexample for these two. So basically there is no relation between invertibility and diagonalizability. Let's just check this. Okay, suppose they say that, okay, A is diagonalizable, and they have even given the, the factorization. So they are saying this and this. Which of the following statements are true? A into this 4 2 plus 1 3. So basically, can you tell me what are the eigenvectors of A using this? Can you tell me what are the eigenvectors? Yes. So Diksha and Saurabh is saying man. No, these are the eigenvalues, Saurabh. Eigenvectors are 4 2, 4 2, and 1 3. Okay. As Diksha is saying. So 4 2 and 1 3. These are the eigenvectors. Now, if you multiply by the eigenvector, then it will be the eigenvalue corresponding to 4 2 is basically minus 1 by 2. Corresponding to 1 3 is 1, right? Then let's just quickly check. This is minus 1 by 2 of this, which means minus 2 and minus 1. Minus 2 minus 1 plus 1 3. It will be minus 1 and 2. Yes, this is true, right? This is true. Is A invertible? What do you think? Using the eigenvalues, can you tell me? Yes, this is invertible, right? So basically this is also true. It is easy question. So both are true. 0 is not the eigenvalue of A. Okay, that's why it is invertible. We can see that A is invertible by observing that A is a product of invertible matrices. Okay. Yeah, that's also fine. Now, you can do this question as an homework. It is easy question, I think. Okay. Now these are the few questions that you can definitely try. Okay. Can you try these questions? Okay. All of these questions you can just try, and then let's just see a new topic today. Is this fine? Because these are the questions which you can actually try. And the answer is on the next page. So that's why I think you can try. Okay. Okay. So now we have seen that there is a given matrix A, right? And then we can decompose that given matrix into three different matrices. So let's suppose this A is n cross n matrix. Then can you tell me the dimensions of this? This will be n cross n. This will be n cross n. This will be also be n cross n. Right? If it is a square matrix, then we can definitely decompose this into three parts. But what is the benefit of doing it? What is the benefit of decomposing this into three parts? The benefit is that this middle matrix, okay, this is the benefit. Okay, so this is diagonal matrix. So if you want to find out power of A, then it is actually very easy. Why? Because you can easily say that power of A will be, okay, this is the power of A. Very easily you can find out the power of A. So in finding out the power of A, okay, this diagonalization is very helpful. You can easily find out the power of any matrix. But it might so happen that in the real life, okay, let's suppose this is real life. In real life, your matrix might not be square matrix. Okay, this is a rectangle matrix. Of size, let's suppose m cross n. Then can you tell me it will be starting from m cross something, right? M cross something, and ultimately uh let's suppose this is square matrix. So this is m cross m, and this will be m cross n, and this will be n cross m, right? Okay. So this is rectangle, that's fine, but that actually diagonal matrix. So it will be easy to handle, okay, compared to this. So basically, if this is m cross n, then ultimately we have, sorry, this is m cross n, so m cross m, m cross n, and then this is n cross n, right? This is n cross n. So these two are square matrices. These two are square matrices. This is square. This is also square, right? This is again rectangle. Okay, I mean the dimension actually you might seem it is square, but it is again rectangle. So what I'm trying to say that if there is a rectangle matrix, then also I wish to decompose this into three parts, such that only the middle matrix is rectangle matrix, and this rectangle is actually easy to handle. Why? Because there will be only diagonal matrix. I mean, this rectangle matrix will be some diagonal matrix, which means let's suppose this is 2 1 0 2 1 3 or whatever, right? And then if this diagonal is complete, then since it is rectangle matrix, then basically you might be having extra zeros. Okay, you might be having extra zeros rows. So basically, this will be the diagonal matrix. Okay, see what I'm trying to say. If a diagonal matrix, if a square matrix is diagonal, then how would it look like? If the square matrix is diagonal, it will look like this, right? If the square matrix is diagonal. But if the rectangle matrix is diagonal, then how it will look like? It will look like this. It has to be diagonal on the principal diagonal, you can say, and then rest of the entries will be zero. So basically, it will look like this. So this is a rectangle matrix which we are calling diagonal matrix. Okay, it will be diagonal on the principal diagonal, and apart from that, every other entry will be zero. Okay, so this is diagonal and rectangle. This is diagonal and square. Okay. So basically, what I'm trying to say that my goal is to achieve the factorization. I want to again decompose, but this time the challenge is bigger. Okay. Earlier, I was having a square matrix. Okay, to start with. Earlier, this was the case, but life is not so simple. I mean, there might be the case that you will be getting the rectangle matrix, and in fact, almost all the time, this is the case. In fact, almost all the time. Okay. So I can say that 99.999% of the time we have to deal with the rectangle matrices. Okay. The word is not, you can say sunshine and, the rainbows. So it is very harsh place. So they will throw you the rectangle matrix, and then you have to deal with this. Got it? So here comes, can you guess it? Here comes what kind of decomposition to rescue? Singular value decomposition. Okay, so now we are going to start SVD, which deals with the rectangular matrices, right? So the goal is to decompose the rectangle matrices instead of the square matrices. Okay, but before that, we have to just look at one process that is called Gram-Schmidt process. We have to look at this process, and then we will be starting SVD. Okay. So suppose, let me just tell you that what is the objective before we start SVD. Let me just tell you that what you want to do. Suppose that you have two vectors v1 and v2, okay, which are something like this, okay, which are like this. Tell me, do v1 and v2 form a basis for R2? Yes, right. It seems like they do form a basis for R2. Now suppose we want a basis for R2 such that the basis is actually orthogonal to each other. I mean every other vector is orthogonal to each other. Okay. So apart from the standard basis we know, but apart from the standard basis, let's suppose we want a basis which is orthogonal to each other. Which means currently we have the basis which is not orthogonal. Like these two vectors are not orthogonal or perpendicular to each other, but we want a basis such that the basis, I mean every other vector in the basis, okay, or the mutually orthogonal, which means if you take the dot product with any vector in the basis mutually, then it will be giving 0. So this is the objective that we want, right? So so what we are going to do now, we are basically going to find out the basis which actually perpendicular to each other. So how to do it? Let's just see. So suppose you have b1, right? Now what we will do, we will say that the old basis we have is b1 b2. Okay. The new basis what we want is something like this. Okay, at least we can keep v1, that's fine, but whatever we want here, it should be perpendicular to v1. Okay, it should be perpendicular to v1. Something I'm looking for which is perpendicular to v1. So what we will do instead of v2, okay, see this v2 is actually having two components, where this v2, you can say one component, it will be the perpendicular. I mean you can decompose this v2. Do you from your 12th class, do you know that any vector you might be writing in I cap and j cap form, 2 I cap plus 3 j cap, something like this, in the x and y form? Do you remember? Okay, so basically if you have one vector, okay, let's suppose 2 I cap plus 3 j cap, then you can definitely break it into two components. I mean multiple components, and every component. So let's suppose you have this v2, okay, you can break it into two components. Let's suppose, do you remember, let's suppose it is theta, then we used to call it v2 cos theta, v2 cos theta. I mean you do not need to know exactly, but from physics you might remember v2 sin theta, thoda bahut. How many of you remember such kind of things? Okay, if this is theta, then we used to say that okay, this is v2 cos theta, v2 sin theta. Anyway, we don't need it exactly, but yeah, that's fine. So basically, what I'm trying to say, that like we will develop the intuition, but let's just see that what is the objective here. So what I'm trying to say, we need to have v2, but such that it is perpendicular to v1. Okay, so we will break this v2 into two parts. One that is aligning with the v1, and one that is perpendicular to the v1. So what we will do, we will take this v2. Okay, so let's suppose this is u2, okay, and this is u1. We want to find u1 and u2 instead of v1 and v2. So let's suppose u1 is v1. Okay, I mean we can keep one of the vector as it is, the starting vector as it is. Now we need to find u2. So to find u2, what we will do, we will anyway start with v2. Okay, we will take the v2. Now v2 actually has two components. Okay, one that is aligning with v1, plus something that is perpendicular to v1. Okay, this is in direction of v1. This is in perpendicular direction of v1. So for example, let's suppose this v2 is, for example, uh something, okay, maybe two vectors. Okay, let's suppose this vector plus this vector. Actually, any vector we will see this little later on. Actually, this is the in between of the topic. So I'm just telling you, but we will see that that's called orthogonal projection. Okay, we will see that after the SVD, orthogonal projection. So basically, you can always decompose this V2 into, let's suppose, two parts. Okay, and one in the direction that is aligning with V1, another that is the direction which is perpendicular to V1. So let's suppose this V2 is x plus y. Okay, this x is in direction of V1. This is it is perpendicular to. Now tell me, if you have V1 already in your basis, then if you want the perpendicular basis, you want to have x or y if you want the perpendicular basis. So what I'm saying, that along with the v1, if you have, let's suppose, x, then this v1 and x in the same direction, I don't think it will work. If you have y, then I think it will work, right? If you have y, then it will work. So v1 and y is something that we are looking for. So if you can break this, if you can break this v2 into two parts, then we are done, isn't it? Let me know. And then we will take this y, right? So basically the objective is that we are starting, okay, we are starting with, let's suppose, some basis v1 v2, and then we want to get the new basis such that in the new basis all the basis vectors are orthonormal to each other. So basically orthonormal means they are perpendicular, as well as they are having the magnitude of 1. Do you know the orthonormal definition? Orthonormal vectors. So we say that u and v are orthonormal when u dot v equal to 0, mod of u equal to mod of v. I mean, this is basically called length of u and length of v. All are one. Okay, these are the unit vectors. So we call them orthonormal vectors. Okay, and what is orthogonal? If they are perpendicular only, this is orthogonal. If we are normalizing them, this is orthonormal. So orthogonal vectors. Okay, if they're perpendicular, we call them orthogonal. But if they normalize also, we call them orthonormal. So our objective is that we want something here which is not only perpendicular to v1, okay, also the magnitude having 1. Okay, I mean, the norm of this particular vector should be just 1. This is the objective. Okay, is this fine to everyone, what we want to achieve? Okay, now let's just keep this on a hold for a minute, and then let's just ask ourselves that why we even want to achieve this, right? See, the objective is that we want to achieve a new basis which is having the perpendicular basis vectors, right? But why we want the perpendicular basis vectors? Can anyone tell me why we are so interested in finding the perpendicular basis vectors? Which means which means my question is that why orthogonal basis is the best basis we can wish for? Yes, little bit. So Tejas is saying multiplication becomes easy. Yes. So let's just see. Let's just first see that why we are wishing for some orthogonal or orthonormal basis. Okay. Suppose suppose that Z is some vector which I'm writing in some not orthogonal basis u1 and u2. Tell me by the diagram, is this u1 u2 orthogonal? No, right? U1 and u2 is not orthogonal. So let's suppose this is multiple. Okay, u1 u2. Suppose this is not orthogonal. So you can write it like this, right? Where alpha 1 is scalar or vector? What do you think? This is definitely scalar. This is definitely vector. Okay, cool. So let's just write it in the vector notation, and then we are rewriting it in the matrix notation. Is this fine to everyone? So ultimately, let's suppose we were interested in finding the coordinates of z in this new basis, okay, in this basis of u1 to un. So which means we are interested in finding out this alpha 1 to alpha n. Okay. So if you want to find out this alpha 1 to alpha n, what is the idea? Maybe you can do the Gauss elimination, right? Or maybe you can find the inverse of this matrix. Something like this, right? Something like this. You can find out the inverse of this matrix or the Gauss elimination, or these kind of things. So whatever you do, it seems little hectic. Okay. Inverse of this or the Gauss elimination, it seems little hectic. We can find out alpha 1 to alpha n, but it's not directly straightforward. But on the contrary, let's just assume that this time we have u1 and u2 as perpendicular to each other. In that case, if you want to find out, okay, so suppose this is perpendicular to each other. Now, in that case, if you want to find out this alpha 1, what you will do? You can just multiply u1 transpose both sides. Interestingly, if you multiply u1 transpose both sides, u1 transpose z equal to alpha 1 u1 transpose u1 is nothing but alpha 1, because these are the, this is the property, this is orthonormal vector, plus alpha 2 u2 into u1 transpose, it will be 0, right? So everything else will be 0, isn't it? So basically finding out this alpha 1 is extremely easy if you have finding out the coordinates in the orthogonal or in fact the orthonormal basis is actually very, very easy. So see here, finding out this alpha 1 is actually very easy. So this orthogonal or orthonormal basis actually makes the computation very, very easy. Okay. If you want to find out alpha 1, then it is straightforward, right? Just this dot product. You don't need to find the inverse. You don't need to find the, the Gauss elimination or something. Just a dot product of these two, and then alpha 1 is ready with you, right? So anyway, like over the time, you will get to know that this orthonormal or orthogonal basis is some best basis that we can base for. And this particular method that we are currently seeing, which is called Gram-Schmidt. Okay, this particular method is actually very popular to convert any basis into orthogonal or orthonormal basis. Okay, so let's just see how to do it. So it can convert this method converts any basis to orthonormal basis. Understood? Okay, cool. So now let's just see what this method does, right? To convert any basis to the orthonormal basis. By the way, these are the two different scientists. Okay, Gram and Schmidt. These are the two different scientists. What do you think that which scientist might be having the, like, just just like, guess which scientist might be having more contribution in this process? Gram or Schmidt? Any guess? Yeah. So Gram was having most of the contribution. Uh, I actually don't even know that why he is allowing Smith to write in this in his own process. But yeah, Gram was the one who has actually developed this process. Okay. Smith had very little contribution, I think, as far as I studied. But yeah, Gram was one who mostly developed the process. Okay. So actually it is a very easy process. So the idea here is that we want to subtract, okay, this b2 is actually x plus y. If we can subtract from this b2 x, then we will be getting y, right? Ultimately, we want y. So what we will be doing, if let's suppose, if let's suppose this is v1, this is v2, then old basis, is b1 b2, and new basis is b1 and something, right? So one thing is clear, that let's suppose this is u2, okay, or maybe let me write u1 here, and u1 is actually just v1 to start with. So u1 you can say it is just v1 to start with, right? Now u2 is little interesting. One thing is clear, that we want to have this v2 itself, but not directly v2. We want to subtract something which is aligning with v1. Okay, which means one thing is clear, that here something like this we will be writing. What it is called? Can anyone tell me what it is called? Can anyone tell me the meaning of this? Unit vector, right? Unit vector along with v1. Great. Yes, unit vector along with v1. So we want to subtract in the direction of v1, right? So we want, see, this v2 is having two things. I don't want this, I don't want this, I only want this. Okay, I'm only interested in this. So v2 is nothing but summation of this thing and this thing. I want to subtract out this, and I will be just getting this. Okay, so this v2 minus something in the direction of v1. Now the only thing that is remaining, that how much I should be subtracting, right? How much I should be subtracting. This is the only thing which is remaining to discuss. And then finally you have your u2, right? Okay. So basically, currently the only thing that we need to find out, that how much we should be subtracting such that you have your u2. What do you think? Do you want to calculate it? Let's suppose this is beta. Okay. Let's suppose this is beta. Can anyone tell me the value of beta? You can use one simple formulation, which is that, see, let's suppose these are the column vectors. So I think the dot product will look like this, right? Dot product, which is v1 transpose, and or maybe new basis, let me write u1 transpose, which is ultimately v1 only, but okay. And then this is u2. It should be 0, right? So which means I think v1 transpose into u2, this should be 0. Is this fine to everyone, what I'm writing here? Let me know. Okay, so basically, ultimately we want some scalar such that this dimension wise also it should make sense, which means it should be v1 transpose and then v2, not v2 not v1 into v2 transpose. It will be wrong. Okay, so let's just see that what is the value of beta such that you have this. Can anyone tell me the value of beta? I mean, you can use the mathematics that you want to use, and then tell me the value of beta. So let's just see, okay? See, if you multiply by V1 transpose, then V1 transpose, remember this V1 transpose is this, right? And V2 is this. So V1 transpose into V2. Is this a scalar or vector? This is definitely scalar. I think every number here is scalar, right? Okay. Every number here is scalar. If every number here is scalar, then then I think this is very easy mathematics. So this is a scalar, I guess. This is a scalar. This is anyway scalar. This is anyway scalar. ओके, सब कुछ ही स्केलर है, तो फिर डरना क्या है ना? तो क्या आएगा बताओ? बीटा into v1 transpose v1 upon v1 should be, you can say, v1 transpose v2, and then from here you can get beta as, is this correct or something wrong? Okay, by the way, this is yeah, tell me what is this? This is also, if you are multiplying this V1 and V1 itself, what is this in terms of norm? So let me just tell you. See, if let's suppose you're writing V1 transpose V1, which means you are multiplying this V1 by itself, right? By itself. Then what is this? Then it will be this number will get multiplied with the same number. Let's suppose this is AB, this is also AB. Then it will be A square plus B square, right? And what is the value of norm? What is the value of norm? Norm is generally square root, okay? Square root of A square plus B square. ठीक है. तो this is square root. This is norm square. This is just norm. Okay. So you can say this particular value is nothing but norm square, right? Okay. So this is by the way called norm. We will see this in the calculus probably. This is called norm of a vector. See, these are the small things. If you don't know, don't worry. You will like we will connect all the dots. See, the thing is that everything in the linear algebra is actually cycle. Okay, so somewhere we have to start, which means that if you are starting with this topic, then probably a little bit information is required from other topic. But don't worry, we will cover them. Okay, we will cover them. For example, here the one information that that is very much required is that how to break down one vector into two different orthogonal projections, right? How to break it down into two different orthogonal projections. This is one information that is required. Now, if I mean not too much required, but if you want to understand this clearly, okay, then it is a little bit required. So don't worry. We will connect all the dots. Okay. So for now, you just study in the flow, and then we will be connecting all the dots as the topic is going to come. Okay. So anyway, so I think you can say this thing is norm square. This is norm. So anyway, this is just a norm, right? So this is norm square. This is norm. So I think this particular whole thing is just a norm of B. Okay. So it will be V1 transpose V2 upon norm of B. Is this fine to everyone? Let me know. Okay. So beta is coming out to be what is denominator? Where denominator in which line you're asking? So this one, right? Okay, let's just do one thing. Maybe see this beta is finally coming out to be. Let me just write it. B1 transpose. This is norm of B. Okay. B1 transpose B2. Okay, if it is seeming scary, don't worry. It will be, very much habitual after the practice. So finally, we have got something like this. V2 minus, you subtract this V1 transpose V2, divide by V1 norm is already there. And then it will be square because these are the two norm into V1, right? This is scalar, this is scalar, this is a vector, okay? And anyway, this is a vector. So this is U2. Okay, let's just do one thing. Let's see if there is any calculation mistake or not. So how we can verify whether this U2 is correct or not? Can anyone tell me? Verify if U2 is correct. Yeah, sorry, it will be V1. Okay, it will be V1. Okay, so I think it was V1. Yeah, yeah, it is V1 only. Okay. So basically, it should be perpendicular to U1 or V1, right? So let's just verify this. Let's just multiply V1 transpose into this V2 minus V1 transpose V2 upon V1 square into V1. Okay. So if you do this, this is scalar, which is V1 transpose V2 minus V1 transpose V2 is again scalar, V1 transpose V2 upon this v1 transpose into v1, this vector into this vector, the dot product will be just a norm square, right? So again this will be a norm square, and norm square is already there, v1 norm square is already there, so it will get cancelled out and finally it is 0, right? So we have verified that it is actually correct. Let me know if that is okay to everyone. Okay, so basically what we are doing, let me just revise it. What we are doing, we have two, we have for example in this particular case we have two vectors, which is v1 and v2 to start with. Okay, now we want to get u1, which is actually just v1. Now u2, which is not exactly v2, v2 minus something which is in line with v1. Okay, so what is that number? I mean, what proportion you need to subtract? Let's just see what was the answer. The answer was v1 transpose v2. So basically, if this is v1, this is v2, or maybe you can write v2 transpose v1, doesn't really matter because this is scalar, right? Since this is scalar, then you can also take the transpose of the scalar, it doesn't really matter. This is v2 transpose v1 or v1 transpose v2, both are fine. Okay, both are really fine. So you can say that the portion that you want to subtract in the direction of v1 will be the projection of v2, which is v2 transpose v1. Okay, divide by norm of b square v1 square into v1. So this is the final scalar that we are getting. And now suppose, let me just extend this. For example, uh, yeah, so instead of writing this also, if you want, you can write it, this v1 transpose v1, because this is the norm square anyway. So let me just tell you, if you want to extend this for multiple example, then what you need to do. For example, if you are starting with x1, x2, x3, this is your start, old basis. Okay, the new basis you want to calculate, new basis. Then the first vector could be x1, the second vector will be x2 minus, okay, the x2 minus some component of this x2, right? Some component, sorry, x2 minus something which is in line with x1. Okay, you want the perpendicular to x1, so you will be subtracting something that is in line with x1, or maybe you can say the new basis, which is v1. Okay, v1. So basically it will be v1 into some constant. And what is that constant? The constant is basically this the old vector projection x2 into v1 transpose, or maybe x2 transpose v1, whatever you like to call, upon v1 transpose v1. Okay, now if you want to extend this, then this is basically v2. v3 will be, if you want to extend this, it will be x3. Okay, I mean x3 as it is, but you will be subtracting two factors here. One that is aligned with v1, okay, because it should be perpendicular to v1. It should also be perpendicular to v2, so that's why there's something which is aligning with v2. Okay, now you see the pattern here, that what is the pattern that we are getting? The pattern is, see here, that if something that is in aligning with v1, then it will be like, it will be divided by v1 norm, okay, or maybe v1 transpose into v1, v2 transpose into v2, and then projection of this multiplication of, you can say, the dot product of the x3, because x3 is something which is we want to remove, and we want to get out of this x3, we want to get the projection we want to remove of x3 into v1 and onto v2 also. So basically you will be removing like this. So for example, let's suppose this is old basis. Okay, old basis is, for example, it is, let's suppose, v1, v2, v3, and new basis I want to calculate. Okay, which is u1, u2, u3. Now what will be u1? Just v1. What is u2? You will be taking v2, but you will be subtracting that is in align with already u1. Okay, because u1 you have taken. So basically it will be u1, and then how to find out this? This is u1 into u1, u1 transpose into u1, and then u1 transpose, basically this v2 projection on u1, which means if this is v2 and u1 you have already taken, right? So you will be writing v2 transpose u1. Okay. And now, if you want to find out, let's suppose u3, then what will be u3? You will be taking v3, but subtracting something that is aligning with u1, and then subtracting something that is in aligning with u2. So, what is something that is aligning with u1? It will be, anyway, u1 transpose u1, here also, u2 transpose u2. Now, this v3 projection on u1, which means v3 transpose u1, v3 projection on u2 also. Okay. So, this is the procedure basically. Now, if this projection is not clear that what is this projection and all, so let's just do one thing. For now, let's just do 2-3 questions, and then maybe tomorrow I will have just dedicated slides to tell you that how to break down a vector into two different vectors and this. Okay. For today, we can just do 2-3 questions to make sure that you understood the process. Can you try to write this u1, u2, u3 by your own? What is u1? Just to start with, u2 is v2 minus something that is aligning with, because you have already taken u1, right? And you want to take v2, but you can't directly take. Then v2 in projection with u1 you will be subtracting. Then similarly, v3 you want to take, but you can't directly take v3 on u1, whatever is there, because you have already taken u1. v3 on u2 you will be subtracting, right? And how much to subtract? This is given by this scalar. Okay. How I got u3? It is just by seeing the pattern. Okay, exactly, the intuition is basically like will be clear when you get to know that, okay, how does the projection work. So for now, let's just do 1 or 2 questions, because I thought that today we can start SVD. So for now, let's just do 1 or 2 questions, and then you will get to know that how to what is the intuition behind it, right? What is the intuition behind this process? So let's just apply this Gram-Schmidt process to get the two vectors. The first vector could be as it is, but they have written it. They're dividing by 1/√2, or they're multiplying by 1/√2. Can anyone tell me why? Because they want the unit length, right? They want the unit length of every vector. They should be orthonormal. Now, what is the second vector? Second vector, you can write it easily. Second vector u2 will be the first vector, whatever is the v1, okay, minus, okay, minus this, sorry, this v2 you want to take, minus, you will be subtracting along with v1. So this is v1 transpose v1, and then this is v2 transpose v1. Okay. Now, if you calculate it, you will be getting your u2. So what is this u2? For example, this is your answer. Okay. This is your answer. If you want, you can do this. Right. Similarly, I think there are multiple questions. Just try this question. For example, you can try this question after writing the formula. So what is the formula? u1 is as it is. u2 is, you want to take v2, but you will be subtracting along with whatever you have already taken, along with v1, right? Or u1, whatever you like to say. Along with u1 or v1, you will be subtracting. If it is v1, then you will be writing v1 transpose v1 on the numerator, and then this v2, okay, v2 component you want to subtract along with the direction of v1. So v2 transpose v1. So basically the projection of v2 on v1. And what is u3? You will be taking v3, but you will be subtracting with respect to what you have already taken, right? Subtracting the component along with the direction of u1, subtracting the component along with the direction of u2. So what are those components? If it is in the direction of u1, then u1 transpose u1. If it is in the direction of u2, u2 transpose u2. Right? Now, what are these numbers? v3, this is v3 projecting on u1. This is v3 projecting on u2. Okay. So this is the formula. Basically, this is a process. Right? Now, if you follow this, for example, they followed it, right? So if you follow this, you will be getting the answer like this. Okay, so there are multiple questions. You can try these questions. This is not very tough question. Once once you are habitual of this, you can easily solve these questions. Yeah, these are basically calculation based question. So just try one or two questions to make sure that you understand the process. Okay, what is this projection? How to break the particular vector into two different vectors? These things we will see so that this particular process get connected. But actually, it was necessary to explain the SVD, so that's why I introduced in between. But yeah, like now I'm thinking that I should have told. Maybe I could have told the projection, orthogonal projection, and these small topics first to introduce this Gram-Schmidt process. But anyway, but the process is okay to everyone, right? I mean, the formula at least okay. Now, what is the exact intuition? These things we can discuss tomorrow. Okay, I will prepare the slides and I will explain this step by step. Cool. So these are the few examples relating the Gram-Schmidt process only. But yeah, now let's just see. Let's just see the singular value decomposition. What is the singular value decomposition and how it can help us to break the matrix, which is the you can say rectangle matrix into three different parts. Now this is a square matrix. This is diagonal but rectangle. Okay, this is again a square matrix. See here, this is m cross n, this is n cross n, this is m cross n, right? So we want to break the rectangle matrix into three parts. Let's just see how we can do it. So basically, let's suppose this is a rectangle matrix. What we can do, we can form two square matrices using rectangle matrix. How? We can use A transpose. This is a square matrix. This is also the square matrix, right? Do you know the similarity between the eigenvalues of these two matrices? Do you know what is the similarity? That this share non-zero eigenvalues, right? AB and BA. So it is just AB and it is BA. So if you notice, this is, let's suppose AB, this is BA. They share non-zero eigenvalues. So you can say non-zero eigenvalues are same. Okay. Now, what is our objective? We want to break the rectangle matrix into three matrices like this, right? So let's suppose, for example, let's suppose we are somehow, okay, we somehow achieve to break into U some rectangle diagonal matrix, maybe 2 cross 3, okay, and then some V. So suppose this A is 2 cross 3 matrix. Assume, okay, let's just assume this A is 2 cross 3 matrix. Then you will be breaking it into 2 cross 2. This is 2 cross 3, and then this is 3 cross 2, right? Okay, sorry, 2 cross 3 and 3 cross 3. Only the rectangle matrix is in between. Now, suppose somehow I am able to break. So, how to find out this U, sigma, and V? Once we find out this U, sigma, and V, then I think we are done, right? So, let's just see how to find out this U, sigma, and V. So, to find out this U, sigma, and V, let's just see that, basically, I'm doing the in the reverse process in the sense that suppose we achieved, somehow we achieved this, right? Then how to find out this U, sigma, and V? Let's just see. Now, this U, okay, the way this SVD works is that this U is basically the vectors which are forming the orthonormal vectors, which means all the vectors are here perpendicular to each other. Okay, so how to find this U, we will just tell you. But yeah, I'm just telling you this vector, this U. Okay, the formulation is automatically such that these vectors are perpendicular to each other. Similarly, in V also, these vectors are perpendicular to each other. Okay, and the sigma will be some rectangular matrix, which is diagonal matrix, which is having some diagonal here, and then zeros at the last. Okay, obviously, still we have not answered that how to find out such matrices that it satisfy all of the properties, which means that age in this three decomposition, U is, orthonorm, I mean, the matrix of orthonormal vectors. This is a diagonal matrix. This is the matrix of orthonormal vectors, like this, right? How to find out this U, sigma, and V? This is still unanswered. So let's just do one thing. Let's just find out if, let's suppose, okay, I'm assuming somehow, let's suppose we achieved this. Okay. Somehow. I don't know how, but let's suppose somehow. Where this U is a matrix of orthonormal vectors. V is also the matrix of orthonormal vectors. Okay. And this is the diagonal matrix, suppose. This is the diagonal matrix. Then tell me what will be A transpose A. Can anyone tell me A transpose A? It will be A transpose will be U sigma V transpose whole transpose into U sigma V transpose, right? This is equal to V sigma transpose. I think, okay, yeah, this is sigma transpose, that's fine. This is V sigma transpose, and this is U transpose. And then this is U sigma V transpose, right? Okay. Is this okay to everyone? Now tell me, if U is a matrix of orthonormal vectors, then what is U transpose U? See, U transpose U will be identity, right? Why? Because U transpose will be something like this. U transpose, and then this is U. So if you multiply this by this, you will be getting 1. If you multiply this by some other vector, you will be getting 0. So basically, this U transpose U is an identity matrix, right? So from here, you got this. This sigma transpose sigma. If you do, multiplication of two diagonal matrices, sigma transpose sigma, then it will be, maybe I can just try doing it. Maybe let's just take it. Okay, let's suppose this is 1, 0, 0, 2. Let's suppose 0, 0. Okay. If this is sigma, then what is sigma transpose? I think it will be 1, 0, 0, 0, 2, 0, right? Okay. This is sigma transpose. If you multiply this sigma transpose by sigma itself, which is 1, 0, 0, 0, 2, 0. Okay. Then you might notice that this will be 1 square, right? And then this will be 0. Then this will be 0. This will be 2 square, isn't it? Is this okay to everyone? Sigma transpose sigma, right? So basically, if you are currently you might not be getting what I'm saying, but let's just see the process. See, A is some matrix which I'm assuming that I'm able to decompose. If I'm able to decompose, then what are these U sigma V transpose, these things? Okay, so this sigma transpose sigma is actually a diagonal matrix, which is a square matrix, right? This is a square diagonal matrix, square and diagonal. So finally, what I'm trying to say here is that if you have, okay, somehow if you have A is this, then A transpose A is coming out to be A transpose A is coming out to be V. Let's just denote this as sigma square. Okay. This is actually the square matrix. Let's just denote it as sigma square, or maybe some other matrix, doesn't really matter. This is V transpose. Okay. If V is orthogonal, then do you remember for the orthogonal matrices, V transpose V is actually identity for the orthonormal matrices, which means V transpose and V inverse are same. So actually this is V into some diagonal matrix, let's just call it D, and then V inverse. So basically A transpose A, you can say this A transpose A is diagonalizable. I mean, you can diagonalize it in this way. So actually my aim was to find out this V. Can you now tell me what is this V? V is eigenvectors of A transpose A. right? V is nothing but eigenvectors of A transpose A, isn't it? If somehow I get A like this, okay, there is no assumption here we did on this A, which means if this is possible, okay, if this is possible, I'm saying then A transpose A is definitely like this, right? Is definitely like this. Now this diagonal matrix, let's just write it sigma square, denote it. Let's suppose I'm denoting it as sigma square. Then if we want to see, ultimately we want to know U, we want to know sigma, we want to know this V. So how to get this U? This is nothing but nothing but the eigenvectors of, sorry, how to get this V? This is nothing but eigenvectors of A transpose A. How to get this sigma? Sigma is basically, here you will be getting the all the eigenvalues. You remember this sigma square is nothing but the eigenvalues of A transpose A. So how to get the sigma? Sigma is square root of eigenvalues of A transpose A, right? Of A transpose A, something like this. Okay, we will formulate it nicely, but for now I'm just telling you in a rough way. Okay, but we are still yet to find U. So basically, let me just revise what I'm trying to say. Let's suppose from this A, I'm saying that we have, let's suppose U sigma V transpose. Then we found out A transpose A is coming out to be V sigma transpose U transpose into U sigma V transpose, which is nothing but V sigma transpose sigma, and then this is identity, this is V transpose, right? So this is nothing but this is some diagonal matrix, or maybe this is basically diagonal matrix such that in the diagonal you have some square entries, right? If sigma is, sigma is let's suppose sigma 1, sigma 2, sigma 3, and all are the zeros in the remaining portion, then what is sigma transpose sigma? This is square matrix sigma 1 square, sigma 2 square, sigma 3 square, right? And all are zeros. Okay. So basically, this is some diagonal matrix where this, in the diagonal matrix, as we know, if I let's suppose denote this diagonal matrix, okay, let's not worry about it is sigma square or something. Let me denote it by sigma square. I mean, like this. Okay, the discrete values, instead of writing it whole sigma square, I'm writing it like this. Okay, I hope that is fine. See, if sigma is this, just tell me, if sigma is this, then can you not find out sigma transpose into sigma? It will be this sigma square, sigma 1 square, sigma 2 square, till sigma n square, right? So basically, what I'm trying to say here is that finally you have got A transpose A, something like this, which means this V is nothing but eigenvectors, because it is eigenvalue decomposition, eigenvectors of A transpose A. These are the eigenvalues of A transpose A. So once you have the eigenvalues of A transpose A, how to find out this sigma? You will take the square root of those eigenvalues, right? See, this is the eigenvalue of A transpose A. This is the next eigenvalue of A transpose A, like that. So once you find out the eigenvalues of A transpose A, then you can take the square root to find out the sigma, which are called singular values of A. Okay. So basically, A transpose A, we got to know it is something like V into some matrix that we have got. It is a square matrix only, because see, this is eigenvalue decomposition, and this is, tell me, this is rectangle or a square? Be it any dimension of A. Tell me. This is always square matrix, right? This is always square matrix, irrespective of dimension of A. Okay. So, this is eigenvalue decomposition. V transpose or V inverse doesn't matter, right? This is eigenvalue decomposition. And then, if you want to find out the V, then it is matrix of eigenvectors of A transpose A. If you want to find out, for example, for this A, okay, if you want to find out the sigma, then this is, sorry, we write it U sigma V transpose, right? If you want to find out this sigma, then this is, yeah, square root of So basically, sigma is nothing but, by the way, this sigma is nothing but, as you know, right? This is nothing but sigma 1, sigma 2, sigma 3, and maybe zeros. Okay, maybe zeros at the end. Okay, this is sigma. So how to find out the sigma 1? This is square root of eigenvalue of A transpose, right? So we know how to find out this V. What we will do, given a matrix, we will find out A transpose A. We will find out its eigenvector. We will be getting V. We will be getting sigma also, right? Because the eigenvalues of A, A transpose A. How to find out this U? This is still pending. So we have, we have calculated A transpose A, which was U sigma V transpose into, sorry, this whole transpose into U sigma V transpose, right? This is what we have done. And finally, we got to know this is nothing but V into some matrix, okay? Some matrix. This is also the square matrix, sigma 1 square, sigma 2 square, sigma 3 square, some matrix into, finally we have got U, V transpose, right? U was eliminated. Actually, U transpose U got, identity. So U was eliminated. So from here, we can only infer V and sigma, but we were not able to infer U. Can anyone suggest me how to get this U? Instead of A transpose A, what we can do? Let's just try with A transpose. Okay. A is this. A transpose is this. Right? Which is nothing but U sigma V transpose into V sigma transpose V sigma transpose U transpose. So from here, you will be getting U sigma. This will be identity. Sigma into sigma transpose. And then this is U transpose, right? So again, what is this U? This is the eigenvectors of A transpose. Okay. So if you want to get U, you can get just like the eigenvectors of. So basically, if you have A, you want to decompose this into U, sigma, and V transpose. Then how to do it? You will be calculating V as eigenvectors of A transpose A. You will be calculating sigma as square root of eigenvalues of A transpose A. Does it really matter whether it is A transpose A or A transpose? In terms of eigenvalues? Because both will be same, right? At least the non-zero will be same, right? And then remaining will be zero if that's required. Okay. And then U will be, if you want to calculate U, then it will be eigenvectors of A transpose. Okay. So basically, this SVD will look like this. I mean, this is you can say the crux of SVD. Yes, there are shortcuts. There are other insights. There are many insights that we will be doing in the SVD. Why we want to do SVD? What is the connection of SVD with the PCA? We will be studying this SVD in very good detail. Okay. But I'm just writing the layout, okay, the sketch of SVD. That suppose if A can be decomposed like this, then how to find out this U, how to find out the sigma, how to find out the V. Okay. And then this sigma is basically called singular values, right? It is sigma 1, sigma 2, sigma 3 like this. Okay, maybe there are zeros at the end, doesn't really matter. So these are called singular values. In gate D, there was a question this time. They were just asking, I think the singular values, something like this. So the singular values, the sigma 1, sigma 2, sigma 3, are actually nothing but a square root of the eigenvalues of A transpose A. So I think the question was this. I think the question was this. They were asking summation of squares of all singular values, which means they're asking what? Summation of eigenvalues of A transpose A. which means they were asking, this is the last year question itself. It means they're asking the trace of A transpose A. Okay. And A was given. Okay. We can try that question later on. I mean, that's easy question. But before that, we need to understand what is SPD. I mean, you can try, like, the objective is not to try this year question. Objective is to make sure that any question that comes in the next year, we should be able to do it, right? Okay. So is this little bit layout clear to everyone that what this SPD wants to do? Little bit, it might be clear, right? That suppose A is decomposed like this, then how to find out these things? See, coincidentally, we tried A transpose A. We got to know, okay, A transpose A is actually a square matrix. Can be having the eigenvalue decomposition, and the eigenvalue decomposition, from that we got to know that what is V, what is sigma. Similarly, we tried A transpose, then we got to know what is V, what is U, what is sigma. So what you do, as an homework also, you just try to find out this sketch, this layout again. You write this U and then find out A transpose A, do the eigenvalue decomposition and see if it is, if it is helping us to find out the V. Okay. Similarly, if it is helping us to find out this U. Okay. So as an homework, can you find out this A transpose A? Can you find out A transpose? These two values. Okay. And just see if it is helping us to find out the A. So basically, I'm just writing it sigma square, but it is the diagonal matrix. Okay. Suppose we want to find out the singular value decomposition of this particular matrix. Okay. So Aditya is asking, it is positive square root or the negative square root? Yeah, it is always positive square root. So here you will be having this sigma square, right? So see, yeah. So like it will always be the positive square root. I will tell you why. Okay, I will be telling you why when we understand the SPD concepts more clearly, that why it is a positive square root. Okay, that's a good question. We will take it. Okay, we will take it. It's really a good question. So let's just find out singular value decomposition as an exercise of this particular question. Okay, let's just find out singular value decomposition here. So what is the first step? First step to find out A transpose and A transpose and A transpose A, right? These two matrices. And then how it will help us? We will find out the eigenvalues and eigenvectors of A transpose and eigenvectors of A transpose A. And then from here, once we find out the eigenvectors of these two matrices, then what we can do? We can arrange them like this. This is U, this is sigma, this is V transpose, right? We can arrange those eigenvectors in this. And then we can get our answer. Understood what we want to do? So basically, the answer is on the next page, but do you want to try? So basically, the detailed answer is there on the next page. For example, this A transpose A is this, right? I think the eigenvectors we are getting for A transpose A, this is the case. This one, okay. So the eigenvectors we were getting is this, but actually these eigenvectors are not ortho. I mean, it need not to be the case that eigenvectors are orthonormal. Okay. Right, because see, for the square matrix it need not to be symmetric. If it is symmetric matrix, then I think it is fine, right? So tell me, it is a symmetric matrix or not? Is this a symmetric matrix, this matrix that you are getting? Why it is not a symmetric matrix? It is a symmetric, right? I mean, it is a symmetric matrix. So the eigenvectors that you have here, right? I mean, sorry, not this matrix, this matrix, right? This matrix A transpose. Okay. Interestingly, this A transpose, will this always be symmetric or not? Tell me, tell me, this A transpose, interestingly, will this be same as its own transpose? Always, right? So you can say A transpose will always be symmetric, right? So the eigenvectors we will be getting here will be perpendicular to each other. So let's just verify. Are these eigenvectors perpendicular to each other? Yes, right? The eigenvectors that we have got of this matrix are perpendicular to each other actually. So you just need to normalize them. Okay. For the normalization, you can divide by the length of this, and the first eigenvector 1 upon root 2, 1 upon root 2. Second eigenvector will be 1 upon root 2 and minus 1 upon root 2, something like this. Sorry for the bright color. So yeah, actually, yeah. So you don't need to actually use the Gram-Schmidt procedure here. Okay. Because the eigenvectors anyway will be always a orthogonal. You just need to see eigenvectors we have got was this 1 1 1 and minus 1. You just need to normalize them, right? If you normalize them, you will be getting something like this. Okay, something like this. Then similarly, you find out A transpose A. Okay, it was A transpose. Then you find out A transpose A, and once you found out A transpose A, then I think, okay, after a long procedure, you will be finding out A transpose A and eigenvectors of A transpose A. Then these are the eigenvectors of A transpose A. Tell me, are these perpendicular? This is 2 minus 2 0, minus 2 2 0, right? Yes, these are perpendicular because the matrix is symmetric. You can just divide by the you can just divide by the length of this, right? You can just divide by the length of this. Okay. So yeah. So basically, I think you can just divide by the length and then V transpose this. Okay. And then finally, the singular value decomposition will be this particular set of eigenvectors, this particular set of eigenvectors, and then in between you will be writing the eigenvalues. So eigenvalues are 12 and 10, let's suppose. Then the square root of eigenvalues you will be writing, right? Okay. And then you can even verify whether this decomposition is correct or not. Okay. So this is the procedure. Now let's just take another example. For example, let's suppose I want to find out for this particular matrix. Okay. Let's suppose for this particular matrix, find SBD, singular value decomposition. Right. Now you know that how to do SBD. You need three matrices. Right. U is the eigenvectors of A transpose A. V is basically having the eigenvectors of A transpose, and sigma are the square root of the eigenvalues, right? Of A transpose A, or maybe A transpose, whatever you like to say. Doesn't really matter. It is the square root of the eigenvalues, right? Okay. So probably the sketch is clear that what we want to achieve here, right? In SBD. So basically, this is the sketch that we say that let's suppose we are able to decompose. Then what are the three possible values here? Okay. Now, tomorrow we will understand the SBD in more detail. Basically, like what is the use of SBD, why we are even doing it, right? And everything about the SBD. Like, I mean, there is something called dimensionality reduction. Okay. So, how it is helping us to reduce the dimension and these things? Everything we will be discussing tomorrow about the SBD. And then you will be extremely confident about the SBD that what is the purpose of SBD, why we even need it, and why it is in so limelight. Okay. Why it is so popular. So, we will be studying this tomorrow. Okay, the more about SPD we will be studying tomorrow. Tomorrow also, most probably, if you like, you can just tell me, because the current quiz is not even attempted by many people. So I'm just asking you, if you like, we can put one more quiz. Okay, tomorrow. Do you want to put one more quiz tomorrow, or maybe on Wednesday? You can just tell me. Okay, okay. So you can just tell me if you want the quiz tomorrow or you want quiz on the Wednesday. Okay, cool. Sure. So we can decide upon this. So thank you everyone. Just just a humble request that you just try this layout once again. Write A like this. Try to find out what is this A transpose A. Try to find out what is this A transpose and see and see if the dots are getting connected in the sense that if V is actually the eigenvectors of A transpose A, if U is actually the eigenvectors of A transpose like this, right? Okay. Yeah. Thank you everyone. Thank you so much. Take care. Bye bye.